Hello everyone, welcome to the past paper discussion. We are in fourth question of this series, and in today's video we are going to discuss the graph theory question, right? So here an interesting case. A company has 6 offices A, B, C, D, E and F. One of the company managers, Nanako, needs to visit the offices. She creates the following graph that shows the distance. All are in kilometers between some of the offices. And first thing, we have to write down a Hamiltonian cycle for this graph, right? So what is Hamiltonian cycle? Each vertex will meet will cover exactly once, and it should be back to the original question. So where we have started, right? So we can take one of the cycle as, let me start with A as usual in chronological order. So from A, I can go to B, then B to C, C to D, then each vertex exactly once, then we can go for E, then F, then back to A. Yeah, E is the best thing. Then E to F, F to A. So, right? So, this is the thing we have taken. So, all the conditions satisfied. Each vertex exactly once we went there, and we are back to the start, right? So, just let's write this down. A to B, B to C, C to D, D to E, E to F, and then back to A. Silent. It is already in an order, right? And that simple it is. Right. And next part is state with the reason whether the graph contains an Eulerian circuit, right? This is also just the 1 mark. Let's Does this have graph has an Eulerian circuit? So what is Eulerian circuit? Every edge exactly occurred once and returned to the starting vertex. So this is the basic of the Eulerian circuit, the two conditions. So first you check, so in order to check if the graph has an Eulerian circuit, check if the graph is connected and check degree of each of the vertex, right? So now why we are checking the degree? All the vertices should have even degrees. If at least one have odd degree, we will say like no, it doesn't have a new circuit, right? Okay, so the graph is connected. That is very clear from this. Every vertex got connected. And then you just check the degree of the each of the vertices. Let me randomly, okay, let's check A first. Degree of A is like how many edges it's emerging from, right? So A, B, A, E, and A F 3. So that's it. No, it's not even, so doesn't have an Eulerian circuit, right? So this graph has no Eulerian circuit. State with the reason. So the reason is since degree of all the vertices is not even. That's simple. 1 mark and moving to the next. Okay, here we have given another description. Nanako wishes to find the shortest time cycle to visit all the offices. She decides to complete a weighted adjacency table showing that the least distance between each pair of offices. So she made an adjacency tabulation, right? And so this shows that least distance between each pair of offices. So like if this is 27 means the least distance from A to B is 27. A to C, the least is 32. Sorry, 52. Similarly, and in this case, we can see some unknowns over here. P, Q, R. This is what we need to find, right? So we need to take the graph. So from, if you are emerging from A, So, okay, what is p-value? A to D, what is the least root, right? So let's just check this from the graph, A to D. So from A, choose the lowest, F, right? So from F to D, I can choose 34 or 22 plus 34, right? So, but I will go with 34 because 22 plus 14 is going to be 36. So better we can go. So A to D, one of the root is 18 plus 34, which gives A to D. One of the root is 18 plus 34, which is 52. Okay, is that the smallest root? No. Let's try in this way. A to B. Of course, it's quite big, like A to B, then this to this. 27 plus 36. For sure, it will be higher. So 27 and 39, 49, 50. So it's like more than that. So I obviously I have A to D. So why I will choose the 54, right? So I'm just ignoring it. The try. Okay. Now the another way is like going in this way, 35 plus 14, like direct root. It's 49. Yeah, I can consider that. A to D. Another way is through E. It's 35 plus 14, which is 49. Right. So that's the shortest route, and I will ignore this. So P value is A to D, the least distance. So P is equal to 49. Right. And next, for Q, this least value. Okay. B to F. So B to F, we have Q mentioned over here. So I can go from B to C, then C to D. Okay, let's see the graph. Okay, here we go. So P is equal to 49 over here. Right, similarly, B to F, which is the shortest route. B to F, like B to 12 plus 22 is like 24. The first one we can observe, it's 12 plus 22, 34. 22, 34. Any other shortest way from B to F? 27 plus 18, of course, it will be higher. And this way, 26, no. So that's the only possible way. And Q is equal to 34. Then, okay, R is given. It is a route from C to F. Let's check for C. C here to F. Let me think the direct route. 28 plus 22, 50. Another way is, okay, 50 is a route. C to F. 28 plus 22. Next. Okay, what if I go from 17 plus 34? It's going to be 51. So I'm not going to take that. And other things are quite, it is very evident, right? So this is the thing. And C to F, R is equal to 50. Right? And that's it. We have completed this. Now, moving forward, Nanoko wishes to find the shortest cycle to visit all the offices, right? So that is what we were dealing with. Now, starting at vertex E, use the nearest neighbor algorithm to find an upper bound of Nanoko's cycle. So we have to pick an upper bound. And we should use the nearest neighbor algorithm. Also, Nanoko is preferring, like her preference is like covering the least distance, right? So we have to start from the vertex E. Let's see. So how to solve this? So like the nearest neighbor algorithm, you start from E and choose the least distance and go ahead in that way. So we should get back to the same vertex. That also matters, right? So let's start. We are starting from E, which is the smallest B. So I will go with E to B. which is 12. Right? Then from B, either I can go A or I can go C, but the smallest I will pick. So B to C. So from B to C. B to C, it is 25. Then from C, I will choose the lowest one, 17, not 28. So C to D is the next path. Then D to E, no, I should cover all the vertex, right? So we can go from D to F, 34. Then F to A, 18. Then I should go back to the vertex again. So I won't go to B. I should go to E. So though it is 27 is lower, we won't go there. We have to go back to E, where we have started. So A to E is the final one, which is equal to 35. Just add it up everything, and you will get it around 141. Right? So this is the upper bound for nanocause cycle using the nearest neighbor algorithm. So quite simple. You start from the vertex and go with the least distance, and you should go back to the same vertex, covering each vertex only once. Right? Fine. And moving to the next. By deleting vertex F, find a lower bound for nanocause cycle. Okay, we have to delete the vertex F and all the connections will got deleted. So how to find the lower bound in this cases? You find the minimum spanning tree, and then you have to add two small edges connecting back to the deleted vertex. That is the way to calculate lower bound. Two small edges connecting, which connects F back to the graph. Okay, now it's time to find minimum spanning tree. Correct? So minimum spanning tree, like I'm ignoring F. I have to go with A, B, C, D, E. I have 5 vertices. So the minimum spanning tree should have 5 vertices, all the 5 vertices, but one less than the number of edges, right? So I need the vertices to be all 5, edges to be 5 minus 1, which is 4 edges should be there, correct? So let's get started. Let's start from E. And I will go for B first, 12. Okay. Then I want to cover C. Like every vertex I should cover, but 4 lines only should be there, right? 4 edges. So then if you go to B to C, then C to D, then it is going to be a loop, right? So instead going there, so B to F, which is 12, then you cover E to D, then you cover C to D, right? And so like C to D, this is covered. Then we can just go from A to B. So see, I have 4 vertices. You just try, use this. 4 edges and 5, all the vertices have been covered. So this is the minimum spanning tree, right? And 2 small edges connecting F back to the graph. So I will pick 18 and 22. This is the way to find the lower bound by deleting a vertex, correct? Fine. So now it is going to be this for minimum spanning tree, and we did this in the graphical part. Now just adding it up. So 17 plus 14 plus 12 plus 27. Then plus you need to add 18 and 22. Adding all these together, you will get 110. Right? And that simple it is. and moving forward. Here the last question. Explain with the reason why the answer to party might not be the best lower bound. Okay, in party, what we got, the recent answer is 110 is a lower bound. Why 110 is not the best lower bound here? Okay, so finding lower bound is like deleting the vertex here, we did, but there is lot of possibilities. I can delete some other vertex which have high weightage and it can result in a better lower bound. So that's the reason. So we can't conclude with one, just removing the removing the vertex F. So, right, we have tried deleting F. Deleting other vertex might give us a best lower bound. That's the reason. So 110 will not work out only for this reason. Deleting other vertex, this is the reason. Might result in best lower bound. Better or best lower bound. So we can't conclude with this party answer. Right? And that's simple. Thank you so much for listening with us. Let's meet in the next video. If you have any doubts or queries, you can post it in the comments. Thank you.